Welcome to this explainer. Okay, if you've ever picked up a fascinating stone on a hike and felt completely overwhelmed trying to figure out what it actually is, well, go ahead and forget the analyst flashcards. Today, we're going to approach geology from a totally different perspective. We are going to treat the Earth like a giant kitchen and look at geology exactly like baking. Trust me, by the end of this, you'll be able to read the ground beneath your feet in a beautifully structured, intuitive way. Let's dive in. To really understand the Earth's kitchen, we first have to nail down the difference between our raw materials and our finished products. Think about a classic chocolate chip cookie, right? A cookie isn't just one magical thing that sprouts from the Earth. It's a carefully mixed combination of flour, sugar, butter, and chocolate chips. Together, those individual items make one delicious cookie. Well, geology works the exact same way. In our geological kitchen, minerals are those pure, single-base ingredients, like the flour and the sugar. Rocks, on the other hand, are the finished cookies, the mixed recipes that nature has already baked together. So, here's our roadmap for today. First up, minerals, the Earth's ingredients. Second, reading the granite recipe. Third, the 3 rock families. And finally, number 4, the endless rock cycle. It's a quick, step-by-step journey to make rock identification super easy. All right, Section 1, minerals, the Earth's ingredients. Before we can start mixing up the dough, we really need to understand the raw ingredients lining the shelves of the Earth's pantry. So what actually makes a mineral a mineral? By definition, it's a naturally occurring Earth material that has a highly specific chemical formula and a unique crystal structure. And honestly, this is a huge realization. When we talk about something like feldspar, we are not talking about a rock. We're talking about a foundational building block. You literally cannot break a pure mineral down into other rocks. It's the absolute base ingredient, just like you can't break pure sugar down into flour.
What's really incredible here is how easily we can learn to spot these ingredients out in the wild. You don't need some massive laboratory. You literally just need your eyes. Here's a quick mineral cheat sheet for the Big 5. First up is quartz. Think of this as the glass ingredient. It's usually clear, white, or just has a very glassy, hard look to it. Next is feldspar. This is basically Earth's flour, the most abundant ingredient, and it almost always shows up as a blocky pink, white, or cream color. Then we have mica, which is incredibly distinct. It looks like shiny black or silvery flakes that can actually peel apart into thin little sheets. Calcite is often white or clear, but its secret superpower is that it fizzes if you drop a little mild acid on it. And finally, pyrite, famously known as fool's gold, with its unmistakable metallic brassy shine. Memorize these visual cues, guys, because they are the absolute key to everything that follows.
Moving on to Section 2, reading the granite recipe. Now that we know our ingredients, it's time to read our very first recipe. And we're going to use the ultimate chocolate chip cookie of the geological world, granite. Okay, so the crucial point here is that granite is not a mineral. It's a rock made of minerals. When you pick up a speckled piece of granite, you aren't just looking at a gray rock. You're looking at a literal mixture. Look closely at those speckles. You'll see chunks of pink, white, or cream. That is your feldspar. You'll see grayish, glassy, hard lumps. There's your quartz. And you'll see tiny, shiny, black flakes. That's your mica. Feldspar plus quartz plus mica equals granite. If you took a hammer and smashed that piece of granite into dust, every single tiny chunk would still contain those 3 base ingredients.
But wait, how did those ingredients get mixed together in the first place? Well, this perfectly illustrates the cooking process of the Earth. Millions of years ago, molten rock, or magma, was trapped deep underground. Because it was insulated way beneath the Earth's surface, it cooled down very, very slowly. And this slow cooling is kind of the grand secret of geology. It gave the mineral crystals, the quartz, the feldspar, the mica, a massive amount of time to grow large and visible. As they grew, they bumped into each other and locked together like rigid puzzle pieces. That's exactly why we can easily see the individual mineral ingredients in granite with our naked eye. If that exact same magma had erupted out of a volcano and cooled quickly in the cold air, the crystals would have stayed microscopic, and we wouldn't be able to spot the ingredients at all. Because those crystals had the time to slowly lock together in such a tight puzzle-like structure, granite is just incredibly tough. I mean, it's everywhere in our daily lives. It's one of the main rocks that makes up Earth's continents. We use it for kitchen countertops, tombstones, buildings, grand monuments. It takes a beautiful polish precisely because it's so uniquely hard and durable.
All right, Section 3, the 3 rock families. Turns out the Earth doesn't just have one way of baking, it actually has 3 entirely distinct geological kitchens. Our first kitchen produces igneous rocks. These are born purely from intense heat. Anytime you have completely melted rock, whether it's magma underground or lava flowing from a volcano, and that liquid rock cools and solidifies, you get an igneous rock. Granite, which we just looked at, is an igneous rock that cooled slowly underground. Basalt and obsidian are also igneous, but they cooled much faster up on the surface. Now here's a huge tip. When you're trying to identify the minerals in an igneous rock, always look at the crystal size. Big chunks mean slow cooling. Tiny specks mean fast cooling. It tells you exactly how fast the Earth's oven was turned off.
Our second kitchen produces sedimentary rocks. I really like to think of these as nature's recycled leftovers. These are not born from melted magma. Instead, they're formed from pieces of older rocks that have been weathered down into sand, mud, or even crushed shells. Over thousands and millions of years, water and immense pressure mash and cement these tiny pieces together into solid rock. Sandstone and limestone are your classic examples here. When you look at a sedimentary rock, you're basically looking at an incredible mosaic of ancient, recycled ingredients. To easily identify minerals in this family, look for rounded, dull grains of quartz that have been worn down by water. Or try that fizz test we talked about earlier to instantly spot calcite-rich crushed shells.
And that brings us to the third and final kitchen. Honestly, the best way to understand this family is with a brilliant little rule of thumb. Bake the rock without melting it.
This kitchen gives us metamorphic rocks. Imagine taking an already finished rock, maybe an igneous granite or a sedimentary sandstone, and burying it deep underground all over again. You subject it to mind-boggling pressure from shifting tectonic plates and intense heat from the Earth's core. But, and this is the absolute key, you don't get it quite hot enough to melt back into magma. Instead, the intense conditions fundamentally transform the rock. The minerals inside literally recrystallize and rearrange themselves. This extreme underground baking takes a regular rock and turns it into an entirely new recipe. The absolute easiest way to identify minerals in these rocks? Look for alignment. You'll often see flaky minerals, like our friend mica, completely squished and lined up into stunning, wavy bands, just like you see in the rock gneiss. Which leads us perfectly into Section 4, the endless rock cycle. This is really the grand unifying theory of the ground we walk on.
Let's look at how this builds a continuous narrative over millions of years, because the Earth is literally the ultimate recycler. These recipes are constantly being rewritten. Imagine we start at year zero with just a loose handful of sand grains, mostly made of that glassy quartz mineral we learned about. Fast forward 1 million years. That sand is buried, and immense pressure cements it together into a sedimentary rock called sandstone. Now fast forward 5 million years. Tectonic plates shift, pushing that sandstone way deeper into the Earth. Intense heat bakes it without melting it, transforming it into a dense, incredibly hard metamorphic rock called quartzite. Same core ingredient, quartz, but it has traveled through totally different kitchens to become entirely different rocks. Pretty wild, right? Now, I know geology can sometimes feel a bit overwhelming, but the magic number you need to keep in mind is 30. We do not need to memorize hundreds of complex, impossible-to-pronounce names to understand the world around us. If we simply learn to identify 10 core mineral ingredients, like quartz, feldspar, and mica, and we familiarize ourselves with just 20 fundamental rock recipes across those 3 kitchens, we are deeply empowered. We'll be able to pick up almost any rock on a hike, look at its texture, spot the ingredients, and confidently identify a huge percentage of what we find. So, here's my challenge for you. The next time you step outside, try not to just walk past the rocks. Stop, pick one up, look really closely at it. Is it glassy? Does it have shiny flakes lined up in wavy bands? Or is it made of tiny compressed grains of sand? Ask yourself, which fundamental recipe is sitting right there in your hand, and what mineral ingredients are hiding inside? The greatest kitchen on Earth is right outside our doors, just waiting for us to read the recipes. See you next time!